So today, in the first half, we'll talk about machine learning and science and electronic structure. But also, I realize I have to get to the DFT part, and there's quite a bit of it. So also in this one, I'm going to talk about using machine learning to do orbital-free density functional theory and the work we've done in that area. So first, I'll give a very quick overview of machine learning and science, and then some recent developments, machine learning and electronic structure. And then the main topic of the lectures is using machine learning to find density functions. So we've had all this from yesterday, how machine learning has taken off, especially in the last 15 years or so, and 5 years ago, it really become dominated by neural networks. Some of the examples I was using were kernel rate regression yesterday, and we'll see we used that at first, and now we don't so much. So the important thing is challenges for physical scientists who want to use machine learning, right? It's really designed for very, and sometimes much more complicated data sets than we have. And physical sciences, you have underlying physical laws. And of course, your algorithms don't know those laws typically. And whenever, if you think about it, whenever you do either experiments or theory, you know when something is wrong with some data you're being shown because you can figure out it violates one of those laws. Like look at a picture, a graph, and you know, and if you're not able to figure it out yourself, you show it to your professor and he tells you what's wrong. So scientists have lots of prior knowledge. That's why you spend, you know, however many years getting a PhD, postdocing and all that. And it's very difficult to put that into a computer. So general purpose machine learning algorithms can easily be nonsense. Another important aspect is that computer science is not a physical science. And publication in computer science is very different from traditional publication in physical science. The standards are very different. People in machine learning, if they have a good algorithm, they write a 4-page abstract. And if it gets accepted to one of these top conferences, that's publishing work, and they don't really care much beyond that. And I would say at least more than half of the papers you see combining machine learning and physical sciences do not meet what we would call basic standards of scientific publication. And by the way, this kind of stuff I added in my talk to, what is it called, Microsoft at Amsterdam, their scientific research facility. And they complained, they said it's far more than that. Right? And so 90% of them are likely, in a sense, to be worthless, right? They're good for the people who send them in and they get them published, and that looks nice, but they'll disappear within a year. They will never be used again. But that doesn't mean that all of them are bad, right? 10% are the first papers doing something, and that something will survive. It will go on and influence what happens afterwards. It's just kind of hard knowing in advance which 10% are to do. But some of them, it's pretty obvious. Okay, so why, we sort of said this already. So they don't get these physical laws. This is what they're saying, you know, if a human had done it. So that's one of the criteria, is if you're using machine learning to do something, you want to do something decent, it should be something that the person could not have done. That's when you know you've done something better. Could you do it without machine learning? And so they actually suggest guidelines, which are, you know, it would be nice if the journals really enforce them. Okay. Okay, electronic structure. We have to keep moving. So machine learned design force fields. So people have been working on this for about 10 years or so. and they're beginning to appear, they're beginning to gather databases. A good friend of mine, Aidan Thompson, visited me last month, and he's the chief developer of the LAMPS code, and the LAMPS code now has a lot of these force fields in it. So he showed us calculations of, I don't know, 1 billion atoms in his simulations using DOE supercomputers. And so that's one thing. And another thing that's coming is, of course, people making these databases. And in particular, I'll talk about the Materials Genome Project. And there are many other applications. And these are two papers off my website where we sort of discuss these things in general. So you can have a sort of static training set. So there are two ways that people make these interatomic potentials. One is where you have several different elements, and you want to be able to capture all the interactions between these elements. And that's often used for drug discovery, many of the lighter elements and a few metals. And then the other application is configurational space in materials, where you might have very simple material like let's say even just carbon, for example, or one of the thing of is copper, and you make a really good force field for copper, and then you can do a simulation with 100 million copper atoms in it, so you can watch a crack propagate. Now, so what is happening is, so the people train by running a bunch of, say, 10,000 DFT calculations of copper and all sorts of configurations, and they use this to train their interatomic potential. That potential often will be more expensive to evaluate even after the training, so that's an issue. So sometimes they're 100 times more expensive than a traditional, analytic force field. So people are now beginning to actually trade expense in computation for accuracy. And then the other issue you have to watch out for is that there are sometimes holes in these force fields where if you're running an MD and it takes a step into a place where the training is not good enough to predict the force, it goes zzz. And Aidan Thompson says, one bad step in 1 billion can really ruin your day, right? Ruin your simulation. There's this anti-force field, and now it's, this is a paper from a while ago, but it's been developed, and it was first trained on DFT data, but now it's trained on highly accurate quantum chemistry data. And they've done 7 million quantum chemical calculations to do it. But yeah, I found this morning. This is a recent review by these guys, and they have, an accurate reactive force field, right, which is something that's been very hard to get. Reacts FF and all the difficulties with sort of getting it to work generally, right? So the difficulties with a traditional classical force field basically doesn't, it works well near equilibrium, but making and breaking bonds is usually very, very difficult, and people have been trying to do that for years. These things do that very well. That's what you're sort of paying for, so then you can do much bigger simulations. So here they're just showing examples of what Annie can do. This one won the Gordon Bell Prize a couple of years ago. This is people like Roberto Carr, Wayne E. Princeton, and Lin Lin is a very good younger mathematician out of Berkeley. And they were doing simulations of water, running DFT calculations, but then they were on the fly learning a potential for the water simulation. And in their methodology, whenever the MD comes to a place where it's not doesn't trust the force field, it goes back and does a DFT calculation and updates the force field. And the way they know when it's not accurate is they have an ensemble of potentials, I think 5. So they have made simply 5 different fits to the potential. And as long as the fits all agree, they say the step is good. And if they start to diverge, then they go back and sample some more. And an application of this, I just saw this, it was from last year, where they claim from first principles, meaning DFT calculation, they see a liquid-liquid phase transition in supercooled water, and they can only do this because they're using this technology, so they can do, you know, huge simulation far beyond what you could do with DFT, because you have to see the phase transition occur. Okay, now what did I do? So because I was too stupid to check the visa requirements, and then I missed my flight by 8 minutes, and then they put me on the next one, and I had a 12-hour layover in San Francisco. So what are you going to do for 12 hours? Well, I remembered I have a young friend. His name is Ekin Kubuk. We call him Dosh. He's Turkish. And he's at Google Brain, which turns out to be in downtown San Francisco. You get there in 30 minutes on the BART. And he happened to be in the office that day. And it turned out Google Brain is another research part of Google. And they discovered, they were told last week, they heard it on the news, that they're being merged with DeepMind. But what his group has been doing, so he's a young guy, but he has a group of about 5 people, and they work on this materials genome project, this, doing simulations to find all sorts of new materials. So he was updating me on their latest stuff. And this is the group of people who've been working on it. It hasn't come out yet. So they, what the funny thing is, so they've been, the people in the materials genome project run all these DFT calculations, and then you analyze them with machine learning to try to predict new stable materials. And it's all these quaternary alloys, and you try to find this convex hull, and you find things that are lower in energy, combinations that are lower in energy than all the others. So I think, they've looked at, I shouldn't say new stable compounds, 200 million compounds. They've run 200 million solid state calculations. They do this with leftover CPU cycles at Google. So they just have it running in the background behind everybody else's job, but because they're at Google, that's still a lot of CPU. So they found, they've run 200 million DFT, I think, no, 200 million. They run a bunch of DFT cases, and they train a force field, and they find 200 million new compounds. 2.2 million of them are stable to the ones that have been found compared to the ones found in the materials genome project. And those guys have looked at about 100,000 or something. So they found 2.2 million that they've kind of missed in the materials genome project. 400,000 of them are stable. And there are, 35,000 known stable compounds, that have been synthesized by humanity since the start of time. 35,000. These guys have found more than 10 times that number, right? So applications. So solid lithium-ion conductors, I think that's a pretty important problem for all sorts of reasons these days. The Materials Genome Project found 21. G-Brain found 528. These lithium manganese transition metal oxygen cathode materials. Materials genome found 1, they found 28. 2D layered materials, again, a very important topic. The materials genome has found about 1,000 of them. They found 52,000. Now, all of these are computational, right? They're running DFT calculations, they do the interatomic potentials from the machine learning, and then they run these things. But they check, and they have something like 75% accuracy relative to the DFT, so they still have vast numbers of compounds. And in fact, they were telling me that I think of these 52,000, the project has been running for a year or 18 months. During that time, of course, papers have been published, and it turns out 500 of these guys here have been synthesized in between. They didn't know about it, but in between, and they were correct. They were stable, but there's 1,000 times as many are listed. But yeah, this is what you can do with Google level resources. Okay, machine learning for making functionals. That's what I want to finish this hour on. So, this was one of the slides that was missing from yesterday. That got built, and we were just talking about, well, here we are, these are the two-dimensional structures, right? And all the stuff that the GBrain are doing is going to go into the public domain. But here, yes, this is a complicated business of calculating acceptance in these 2D materials with all sorts of industrial applications. So this was my example that I missed for the applications of DFT. Okay, so almost all the machine learning for functional in the literature takes existing approximate forms. So all the stuff I talked about in the first hour yesterday were human-designed approximations. And they have limitations, and the people try to make better versions of the ones that other people have made. But they're still approximations, and they fail in difficult cases. And we had mentioned that if we stretch bonds, they often fail. So almost all the work I've been involved in, instead of looking at the density at just a point and its gradient, you look at the entire density and try to create essentially the exact functional to a given level of accuracy. And when we do that, we can solve problems that essentially almost all existing functionals fail for, especially these problems of strong correlation. Okay, so orbital-free DFT means learning the cone-sham kinetic energy. If you know that as a function of the density, you don't have to solve the cone-sham equations. So the first paper we did in 2012, and this is with Klaus Robert Müller, who's a guru of machine learning, and a very good postdoc of his, Matthias Rupp. And they were just starting to explore applications in electronic structure. So we simply take a box, and we're going to look at non-interacting particles, and we put a potential in the bottom of the box that's a sum of 3 Gaussians. Then we take with a grid of 500 points in the box, solve the Schrodinger equation. These are random variables, so we do 2,000 realizations of this box problem. And then we train a kinetic energy functional, and I hope that you were here yesterday, you recognize back in the day we're doing kernel ridge regression. And we take a Gaussian kernel, which is pretty standard. But you see here, inside here, we have this integral of over space of the difference between 2 densities squared. So this kernel is a totally non-local object because it's, you have to integrate over the whole system, and it's measuring how different two densities are, one from the other. And what you do is you sum over all your data points, and you have weights and kernels. And so the kernel, if two densities are identical, this is 1. And then as the further you get away, the more rapidly this decays. So what happens is you take some density, and the densities that look most like it will contribute most heavily to your estimate of what the kinetic energy should be. Here are some examples. Here's one potential, here's another out of the 2000. This is with 4 electrons in the box, this is with 1. And so that we consider the exact data, and can we make a functional that will reproduce this? We could. But one thing that we realized, I think I may have gotten a little lost there, is when you do orbital-free DFT, as I mentioned yesterday, not only do you want the energy, you need the functional derivative, because you find the density by solving this Euler equation. So if you have the functional, you can differentiate it and solve this equation, but you need to have an accurate derivative. And if you think about it, if you interpolate a function over a bunch of points, you can get a very accurate fit to those points, but you might be inaccurate for its derivative. And it turned out the derivative, you can't see it here, is hopelessly inaccurate when you do this interpolation. Well, what they figured out what to do, Matthias and a very good student, John Snyder, is we did a principal component analysis, and we would project the densities, the trial densities, onto the directions in which we had data, in which there were data. And when we did that, you could get a much more accurate derivative. So this is this projected derivative, and there's a red line and a black line, and they're almost on top of each other. So when you do this projected derivative, and then we had to figure out how to optimize it, how to go downhill with this projected derivative, but then we could get very accurate results. Okay, that doesn't seem to have the picture of the results. So within a few weeks, the guys were able to get, with about 100 training points, chemical accuracy in this little problem. So this was just a proof of principle, right? Showing that you could use a standard machine learning method to design a functional which had chemical accuracy. But no one probably in this room cares about 4 non-interacting fermions in a box in 1 dimension, right? This was just a toy problem. So going from this, right, you want to go all the way to large systems, right? And at the moment, I'd say we're sort of here. We aren't quite here. And I'll show you in the rest of the next 10 minutes where we are. So the next step was designing, doing this for a real molecule. And first we did it for water, and then we did it for slightly larger molecules. So we're going to skip over these things. This is us testing various things. So we always make these plots as a function of the training data to see learning curves and check that the errors go down. This is for H2, and we check that we got chemical accuracy relative to the DFT calculation. So we're using using it as a DFT where the exact answer, which it isn't. There's water where we get both the density and the energy, right? So the basic step forward here was instead of learning, we discovered our projection method got too expensive when we went to more complicated systems. So instead, we learned both the energy and the derivative of the energy. So a vector of numbers rather than one number. When you think about it, it's kind of stupid to learn the energy and then differentiate the fit. It's much smarter to learn the derivative. And then, actually, I have a movie, but I guess the movie is gone. Oh, wait, it's still here. Amazing. Let's hope it doesn't break it. Oh, there it is. So we did a sort of gas phase molecular dynamics, and this is malinaldehyde. And here it is. And so this is a hydrogen atom, and what's happening is it's transferring from one oxygen to the other during the simulation. And what was cool about that was, so this simulation was run entirely with the machine-learned Holmberg-Kohn map for the kinetic energy. And yeah, what's nice is that the proton transfer was not in any of the data. What happened is we trained it and we tested it, and then we ran the simulation and saw this proton transfer occur, even though we hadn't trained for that. And that was with Mark Tuckelman and Leslie Folk-Marcano. Okay, at NYU. And then a little bit later, we created this thing called delta DFT. So this is sort of pretty much the same setup, except we decided to, instead of training on DFT energies, we would train on much more expensive energies from quantum chemistry, CCSDT. So this is just the example of water, and compared to the DFT calculation was pretty good for equilibrium water, but if you stretch it or compress it a lot, you start to get substantial errors. And this is mean absolute error near equilibrium, I think, as a function of training samples. And this is the DFT result, which ends up with a 2 kilocalories per mole error. This is the couple cluster result going to right answer. And what we did was we did what we call delta DFT. So there's this trick in machine learning, delta learning, where you train on one problem and then you use the fits. You may adjust some of them to apply it to a more difficult problem. So here, what we learned was the difference in the energy and the forces between the density functional and the couple cluster. You can see that this learning curve is much faster by the time, you have almost no error by the time you have just 20 training samples. It's much easier to learn the difference between the two than either of them separately. This is just a potential energy plot, as in terms of the angle and the distance, and you see that it's much smoother if you just look at the difference between the two functions. This is the minimum. Okay, that's the same. So we did this for resorcinol, a more complicated molecule, and we picked this on purpose because if you look at the difference, I think this is the PBE functional, and the quantum chemical rotational barriers, you see it makes a substantial error in the barrier to rotation, the DFT, and we wanted an error so that we could show the difference. And then when we run the simulation, we do the simulation having trained on the DFT, and the simulation having trained on the difference to get the couple cluster result. And you see that in one case, the thing rotates and goes over the barrier, and in the other case, it doesn't. in the couple cluster case, it rotates and then comes back. These are the trajectories. And we can see that if we run, so in this case, you run the DFT simulation and to within 1 kilocalmole or less, very high accuracy, we can make the DFT calculation produce the trajectory of a couple cluster, which would be too expensive to run the molecular dynamics for. So that was with Felix Brockert, one of Klaus Mueller's students. And then this is the one that's in preparation and we'll look at this evening. So we're trying to get this one finished. This is our draft from about a month ago. And I guess there's been a slight degradation in resolution here, but that's good because our calculation is not great, right? So this is our friend again, resorcinol, and this is the vibrational spectrum of resorcinol extracted from running an MD simulation for a long time, right? So to pull out the vibrational spectrum, you have to run it long enough for all the modes to have explored their little bit of phase space. You get the dipole moment and Fourier transform of the spectrum. And roughly speaking, right, this is compared to experiment. I guess the blue is the DFT, the orange is the experiment. You can see that it almost perfectly, not perfectly, but more or less agrees. It has the vibrations in the right place and stuff like that. So what's important here is, so we have this new way of so in our previous work, we hadn't bothered worrying about the symmetry. And so then we would do the enhancement by flipping the molecule and all this to data enhance. Now, Mihail Pawlowski, who's the new graduate student on this, has a new way of representing the density that's equivariant in terms of the symmetries around the atoms. And we use that also to find, to characterize the energies, forces. So it's actually much more efficient than our old things, and also, you don't have to enhance the data. And then when we run, so we do the learning and we run this for the resorcinol, it would be nice to compare this with the DFT result, except we can't afford it. And I'm not sure anybody, well, probably Google can, to run that an MD simulation long enough to see all those modes, to see if there's any difference. So that's why the comparison is with experiment. Okay, so this work is ongoing and hopefully we'll finish it in the next month or two. Okay. So summary. So there's lots of bad papers using ML in science, but that doesn't mean that there aren't good ones, right? Yes, so for the students out there, don't add to this pile, to the pile of bad ones, right? Try not to. These machine-learned interatomic potentials are beginning to be used all over the place. And maybe they'll put the regular DFT out of business. All you need DFT for is training. I don't think that will happen, but we'll see. And then we also saw, it's not in the summary right now, this materials genome project is really beginning to take off. The results from Google Brain. And then the bit that we had done is gotten this far with orbital-free DFT. So the crucial point is, in these simulations, especially like when the proton jumps from one to the other, there's no way that a traditional force field could have done that. And any semi-local type approximation for the kinetic energy function will fail completely as you stretch the bond. It will go completely wrong for the same reasons that the exchange correlations go very wrong when you stretch the bonds. but you can learn the functional for that case. But it's only for a specific molecule, right? If we had done a different molecule, we would have to redo the training. So you give me another molecule about the same size, I can make another functional which will work for that molecule. But that isn't really good enough, right? Your human designed functionals, you can apply them to any molecule. So, and the problem actually comes from looking at the entire density and making the functional that way. What you really need is to know the features in the density that would give you the same results without studying the entire density, because once the system becomes really large and complicated, you can't be relearning your machine learned functional every time you swap one atom for another. I mean, it does transfer a little bit, but it doesn't really do it well. Okay, and I'll stop here.